I'd like to introduce Anne Moree, who's going to talk to us about the effects of ocean warming and deoxygenation on marine species. So over to you, Anne. Thank you.
Thank you so much, Adrian. So I'm Anne Moree. I'm based in Switzerland, in Bern, and I will now start sharing my. You see my presentation? Adrian, you are muted. Thumbs up?
Yes.
Great. It's not the first slide. So, yes. So I want to show you some results which were recently published in Biogeosciences on the impacts of ocean warming and deoxygenation on marine species over the course of the 21st century. And this is a cooperation between me and Professor Thomas Fröhlicher, also in Bern, and two marine biologists from the University of British Columbia, Taylor Clark and William Chung. And initially I promised Adrian to just show you these results, but I have some recent results which connect really well to this. So it's what I'm currently working on and writing up. And it's on long-term impacts of global temperature stabilization and overshoots on marine species. So I will give you a little bit peek view towards the end of my talk into that topic as well, which uses really the same methods and same marine species. So if I talk warming and deoxygenation, I first want to give you a feeling of how much warming and deoxygenation we're talking about until now and into the 21st century. So observations show that for sea surface temperatures, that these have on average globally already warmed by about 0.5 degree since the 1960s until now. And if you look at large Earth system model simulations from the CMIP6 ensemble, you take a high emission scenario, SSP 585, between now and the end of the century, you get an average further increase of about 3.5 degrees at the sea surface. So really profound warming, and here in stippling, it's a model robustness. So these are really high results with high confidence. So for oxygen, the story is that there's a general decrease expected into the 21st century from model simulations, although less robust. So you see here no stippling in the equatorial region, so it's more uncertain. And also that the marine oxygen inventory likely already lost about 2% since the 1960s until now, and that this is really thus increasing following model simulations. So with this in mind, I really phrased the questions, how does this warming and this loss of oxygen potentially impact global habitat viability? And what is then driving that? And how do these changes impact the habitat volume of contemporary habitat volume of marine species? And again, what is driving that? So in order to quantify the impacts of these changes, we use an index called the Aerobic Growth Index. It was recently developed and published by one of the co-authors, Taylor Clark. And I will give you more detail on this index in the next slide. But for now, it is simply the oxygen supply over oxygen demand for a species. It's a species-specific indicator. And oxygen supply is really just environmental oxygen, while oxygen demand depends on temperature and species-specific features. And together, if you calculate this index for an individual species, you can get an idea how oxygen and temperature combined impact habitat viability of a species. So whether a habitat of a species is viable to sustain a population of that particular species. And that's exactly what we did. So we have a good tool at hand, but the next question would be, what kind of data did I use? And I'm a modeler, so I went to the CMIP6 model ensemble, and we selected 6 with the available data. But of course, model biases are or can be profound. Really depends on the model. So we have bias correct them using observations, also drift corrected them. And using such Earth system model data, we really get a sense, having 6 of them, of both the model uncertainty, and also we selected 2 different scenarios, a high emission one and a low emission one into the 21st century. So we get an idea of scenario uncertainty as well in our assessment. So we calculated this index to find whether habitat viability for species is changing for 47 different representative species. And I just selected here six random ones to just give you an idea of what a distribution of such a species would look like. And these are selected such that you have a really diverse range of habitat size, depth level, body size, climatic zone. And they actually cover the epipelagics, top 200 meters, mesopelagic, which we consider from 200 to 1,000 meters, and an demersal zone where we really take the sea floor or the bottom data from the model output. So a little bit more information still on AGI before I show you some results. AGI, as I told you before, is this ratio between oxygen supply and oxygen demand. And oxygen demand, if you look at it a bit more closely, so this is the species-specific part, really just consists of an oxygen threshold, species-specific, a temperature preference, species-specific, and then it is influenced by temperature, environmental temperature. So actually, when temperature increases, when it's warming, the oxygen demand increases for a species. And all these in black are really scaling constants, which are the same for all species. So I chose AGI because it integrates both temperature and oxygen in one index. So many studies before just tried to assess what could warming do to species, how would oxygen loss impact species, and here you manage to assess it in one. And you really only need temperature, oxygen, and distribution data for a species in order to be able to calculate this index. And despite that, it's in really good agreement with other indices, which are similar but require way more species-specific information than this one. But they agree really well with each other. So we can calculate this AGI, but you probably wonder, okay, but when do we get impact, right? So you need some critical threshold below which you say, okay, now this index, which summarizes both oxygen and temperature influences, is so low that a species cannot sustain a viable population there. So we do this following earlier approaches, and we take the 10th percentile of all AGI values in the species habitat. So you go and take the data within the habitat of the species, you take the 10th percentile of that, and you say, okay, below that, a species is likely unable to sustain a viable population of that particular species. And of course, this value is uncertain, but a really strong argument in favor of it is that the real distribution of this curve, if you actually plot it for a specific species, is quite skewed and quite steep here across this 10th percentile. So really looking like this AGI value around the 10th percentile acts as some form of a threshold for the species. And below that, there is very little, so the species is not able to sustain a viable population there. So we have a threshold, we can calculate AGI, and now we can finally get to the results. So I want to start showing you relative changes in AGI, and there are actually entirely species independent. So let's zoom out a little bit to just get a feeling of how is AGI changing towards the future, and therefore how is habitat viability changing across species. And I show you here for 2 degrees of global warming versus the contemporary. So 2 degrees of global warming is fortunately in the future. And at 3 different depth levels, how AGI is changing. And overall, it's blue, right? So it's decreasing, more so at the surface. You have really strong, it's heterogeneous, so you can really see that it matters where you live as a species. And these hatched areas are actually where the models disagree in sign even, and also in magnitude. So the CMIP6 models have in certain areas, they're just not robust, but outside they look quite robust, and they show this general decrease in AGI. So the first question I asked when seeing these maps is, okay, but what is then the contribution again from oxygen changes and temperature changes? So the warming and the deoxygenation. So I was able to split it up into the contribution, so the same map, but then the contribution from oxygen and the one from temperature. So for oxygen, like I showed in like my second slide, is relatively uncertain across the models, and you see so you see more hatching, but you see also that at some depth levels, like the mesopelagic, oxygen decrease is a large contributor to these losses in habitat viability. And for temperature, you see the influence is the largest at the surface, or the epipelagic, so the top 200 meters. And that really makes sense, right? Because the warming anomaly coming from the atmosphere has equilibrated more with the top 200 meters than it has with the deep demersal seafloor waters, unless it's at the coast, because then demersal is actually very shallow. So going from here, I wanted to really say, okay, but how about these individual species? These 47 species we looked at, how is their habitat volume, their contemporary habitat volume affected by such changes, relative changes in AGI? So I show you here for all of these 47 species and 2 levels of global warming, relative changes in habitat. So you have a contemporary habitat size, and I say, okay, what new volume has been exposed to these subcritical levels? So below AGI crit, which I introduced to you before. And if you look through this figure, I mean, the y-axis here are of course everywhere the same. You see most changes are below 5% RIN. So small changes in contemporary habitat volume. Although for individual species, this can be way larger. So especially here towards the left in the epipelagic, you see a few species losing about 25% of their contemporary habitat, which is really profound, especially because many of these species are top predators. So they are really central in their ecosystem, play a central role. The box plots here really give the uncertainty in both model uncertainty and scenario uncertainty. So of course, there are a lot of uncertainties behind using model data and not knowing what the scenario is going to be, but you really capture all these in these box plots. So it's quite profound, I would say, for individual species. If you see the little black stars, they're actually the median contribution from temperature to this change. And the median in the box plot is the little orange bar. So you see actually for most species, the change is almost fully due to warming. So temperature changes. So this relative expression of habitat change, or relative to their contemporary volume, facilitates comparison between species. But if you're interested in absolute losses, because, for example, fisheries right in front of a coast, it's way more relevant where and how much volume is lost than relative to the complete habitat size. I made the same plot, but then in cubic kilometers. So the ordering of the species is entirely the same. And what you see happening here, and note that now the y-axis are not the same because the volumes in these three different depth levels are just so different. But just to highlight the epipelagic here, the species that were in the previous plot towards the right, so with very, very small relative losses, are now the big losers here with very large absolute losses. And that makes sense because they are very wide-ranging species. So they live more or less everywhere across the globe, many tuna species, for example. And even though a few percent of their habitat might not sound like much in absolute terms, it is in cubic kilometers. So we found really in the study that this loss is generally below 5%, but that for individual species, the impact can be much higher. And this really confirms a lot of other studies that have shown this contrast, that some species are really not so vulnerable to climate change in the form of deoxygenation and warming, and others respond very strongly to it. So they have a different vulnerability. And exactly this vulnerability concept I wanted to explore a bit further. So our question was, why are the contrasts so large between these species? What is driving the differences between these species? And in order to make you understand or show you this vulnerability concept, which we then developed, I go back to this PDF of which I showed really a schematic when I was explaining AGI. But now I plotted it for an actual species. So this is an Atlantic tuna living approximately here. And this black curve is probability density function of all the AGI values in this species habitat. And then, as I explained to you before, this 10th percentile is the critical threshold of this species. So here in gray. And if we now do a hypothetical decrease in AGI of 0.1 units, we move this whole curve, and you see the stippled area gets exposed, newly exposed below the critical threshold. So you can imagine that if the shape of this PDF is different, you get a different exposure. And that's exactly what I will show you. So we could quantify this by taking the cumulative sum of this PDF, then you get your CDF. And if you take the slope at the critical value, you really end up with a number that is change in volume per change in AGI, right? And this slope is exactly what is very different between species and what we use to quantify vulnerability. So without not too many steps, we have a way to quantify vulnerability to oxygen and or oxygen changes and temperature changes. So just to give you an idea of how different can be, here we have the big eye tuna living more or less everywhere. And the original PDF here in black looks like this, and you already see there's quite some distance here from the AGI crit value. And if you do the exact same move of 0.1 unit of AGI, you expose much less habitat below the critical value of AGI. So for the exact same change for this species, for the exact same change in AGI for this species, you realize only a change in volume of about 1%, and for this species it's 9%. And you see that also from the difference in slope. So what I found really interesting from this concept is that it really explains about 85% of the variance in relative habitat loss. So the species, they vary in how much habitat loss they have, but this can mostly be explained just by this vulnerability concept. And moreover, it's not the absolute changes in temperature, so the amount of warming in a habitat or the amount of oxygen loss or how big the relative changes in AGI. They are all actually quite poor indicators of habitat loss. So a habitat can warm quite a bit, but if the species is not vulnerable, nothing will happen, right? So that's intuitive as well. So before wrapping this up, I show you a bit of a teaser of the work I'm writing up right now. And then I summarize and finish my talk. Yes, so I use the same approach with AGI, same species, to then look at long-term impacts of global temperature stabilization and overshoots on marine species. So what we managed to do, first focus on the top two plots, is to force an Earth system model, the GFDL ESM2M model, into different stable temperatures. And you see these are really long runs. So you start late 19th century, you go to 2500. And using this new approach developed within the group, we can stabilize temperatures at different levels. And we can also force the model through a temperature overshoot. So this is really a different way of using Earth system models, which is really brand new, because before these Earth system models in CMIP6, for example, were always emission forced, right? So you give it a certain amount of greenhouse gases, and your question is, how warm is it going to be? And now you turn it around. You say, okay, just organize something with the emissions, but get me that temperature. And the model stabilizes around a certain temperature. So from these runs, we could then ask the question, okay, for these species, what is then median habitat change for such a temperature stabilization? And after an overshoot, is there still something happening in the ocean, right? So what we found is two main conclusions on this figure is that if you look here, for example, say 3-degree temperature stabilization, after this temperature target hit, which for politicians in the atmosphere, right, like Paris Agreement is 1.5 degrees of warming. So you've met your goals on a political level, global mean temperatures at 1.5 degrees, everyone happy, it stays stable there. But the question would be, what happens still in the ocean? And as the ocean is way slower than the atmosphere, it has still to see most of the atmospheric anomaly and adapt to it. So you see here that a major part of the habitat loss for these species is yet to come after hitting the temperature target. So even though the atmosphere is stable, you still have here continuing decline. And that's valid for all these scenarios, but I just highlight the 3 degrees one for clarity. So for the overshoot, we really asked, okay, in the atmosphere, after it has returned within the variability of a 1.5 degree stabilization scenario, so either going directly to Paris Agreement 1.5 degrees, which is unlikely, unfortunately, or overshooting, the atmosphere is back in the same state, but do we see a difference in the ocean? And there is, so this is again median across the species, there is a significant negative legacy across these species after an overshoot, even centuries after returning in the atmosphere to a set target like 1.5 degrees. So with that, I want to summarize. I introduced you to AGI, the aerobic growth index, which really nicely integrates both oxygen and temperature. I can, using this AGI, assess the viability of a habitat to sustain a particular species. And I show you that it's both warming and deoxygenation that reduce habitat viability. across species. That for individual species, losses are generally below 5%, but for individual species, this can be up to 5 times higher or so. And this really depends on the species and also a bit on the level of warming. And that we really understand these large differences between the species through this concept of vulnerability, where this concept really explains most of the variance in habitat loss and this relative loss of habitat, as opposed to the amount of warming or oxygen loss or relative changes in AGI. And I, of course, gave you a little teaser. So with that, I want to wrap up and open up for questions.
Excellent. Thank you very much. Yeah, very, very interesting. So I think we've still got time for a couple of questions, maybe. So if I go to the chat, I can see that the fastest person off the mark was Ken. Ken, do you want to ask the question, or was Marina answered your question?
Marina kind of answered it. A lot of the drivers seem to be biological, and I'm not sure how well these models can capture changes in production and export that would drive the oxygen cycle.
So your question is whether these models can capture changes in oxygen into the 21st century.
Out to 2500, let's put it that way.
Yeah, if we look at the teaser part. Yes. So the thoughts on that in the literature are that models likely underestimate deoxygenation, so losses would be bigger than what I've assessed here. But I've also shown you that for this index, it's mostly temperature impacting the losses. So even if you would have a double as high oxygen loss, you still get mostly temperature impacting the loss in habitat. So I think the temperature projections are way more reliable, especially after doing my observational bias correction, right? So I used World Ocean Atlas data and I subtracted that bias from the model. So I only used the model trend really in the end. I would say this would be then a conservative estimate of what would really happen, so a lower estimate.
Excellent. Thank you. So maybe we can squeeze in one quick more question. So Malin, did you want to ask your question?
Yeah, sure. Thank you. Thanks, Anne, for a great talk. So as far as I understand it, this AGI index is kind of habitat loss in terms of the whole species. So my question was whether it takes into account the supply demand requirements at different life stages, or is it mainly for the adult individuals? Because yeah, I mean, they might not even live at the same depths, sort of the larvae and the eggs and yeah.
Yes, so by the makers of AGI, they are exploring this a bit now. When I asked them about exactly this, like, could we split it up into a seasonal AGI and then look at whether AGI is maybe subcritical in an important phase of their reproductive cycle or whatever, and also this part of location and body size, but they say that is not possible at this point in time with such indices. For that, it's too generalized, and also the temperature preference and oxygen threshold would be specific for a life stage. So you can, this is really a population. So whether a species can sustain a viable population of that particular species. So that includes the entire thing. It's really zoomed out. Yeah.
But that's better, so that's good.
I don't know.
Excellent. Thank you very much. I'm sorry we don't have time to go through the other questions. So Anne, you know, I'll send you the ones that are in the chat after the call, and say if anybody has any questions for Anne, I'm sure she would be happy to receive any questions by email. So thank you once again, Anne. Excellent talk.
Yes, you're welcome. I will stop sharing.
Thank you. Moving on then. Thank you